everyone, welcome to BCP Med. In this video, we are going to be taking a look at the atomic property known as electron affinity, which describes the energy associated with electron capture. We are going to discuss what factors affect its magnitude, including the complicated effect of atomic radius, the periodic trends associated with it, and some group exceptions associated with orbital effects. Let's go ahead and get started. So, what is electron affinity? Well, as the name would suggest, it's how much an atom wants an electron. But to avoid anthropomorphizing an atom, electron affinity really is the electric potential energy change experienced by an atom when it captures a free electron to form an anion. So we can also think about it as the energy of anion formation. Electron affinity can be expressed as a chemical equation of X plus an electron gives X minus, the anion, which is the converse of the definition of ionization energy, which is an element losing an electron. A unique fact about electron affinity is that it is almost always going to be negative, which means that electron capture is almost always favorable energetically. Why is that the case? Well, if we look at the electric potential energy equation here, we see that potential energy is related to the charges present in a system, including their signs. Let's now imagine a free electron approaching an atom. One charge associated with the new potential energy is going to be the new electron itself, which is always negative, and the other is a combination of the electrons and protons in the atom. If you remember our discussion on effective nuclear charge, you see that the outermost valence electrons do not repel one another very much, and that carries over to our incoming electron. The current valence electrons will not repel it very much, and so in our equation, the atom as a whole is going to behave like a positive charge equal to the effective nuclear charge. Because the incoming electron is negative, and the atom with an effective nuclear charge behaves like a positive charge, their product is a net negative total potential energy, meaning the electron capture is energetically favorable. Predictably, since the atom behaves like a particle of charge Z effective, or Q in this equation here, as circled in red, electron affinity is going to experience a periodic trend related to the effective nuclear charge. An atom with a larger effective nuclear charge, say +7 like the diagram below, will have a larger electron affinity than the atom with the Z effective of +1. In other words, the +7 charged atom will experience a larger drop in energy due to electron capture. Or, yet another way, we will have a more negative electron affinity than the +1 nuclei. We can see this trend pretty clearly if we look at the period 2 nonmetals. Clearly, the magnitude of the electron affinity becomes larger and more negative generally as you move towards the right, mirroring the increase in effective nuclear charge. Obviously, something weird happens with nitrogen, but we'll talk about that later. But again, generally, as you move towards the right-hand side of the periodic table, electron affinity tends to increase in magnitude, becoming more negative to parallel the increase in effective nuclear charge. Now, the relationship with atomic radius is going to be a little bit tricky. As you can see from our electric potential energy equation here, radius should affect the electron affinity since it affects the binding energy of an electron to the nucleus. This is certainly the case, but the trend is actually quite a bit more complicated than was seen with the effective nuclear charge directly. The first relationship is simple, and it involves the incoming electron and the nucleus alone. The amount of attraction between the electron and the nucleus decays with a 1/r relationship with increasing radius. So larger atoms are going to have a smaller magnitude electron affinity based on this, since there is going to be a smaller binding energy associated with electron capture. Thus, we would expect electron affinity to decrease going down the periodic table, approaching 0, becoming less and less negative. The other effect is a bit more nuanced, and that is the fact that electron repulsions are at play as well. As an atom gets larger, the space the electrons have to move increases, so they can become further apart from one another, minimizing the amount of electrostatic repulsions. Conversely, smaller atoms experience far more electric repulsions. As such, it's easier to add electrons into a larger atom, so electron affinity magnitude should increase going down the table because it's more favorable, or rather less bad, to add electrons into a larger atom. Clearly, these nuclear and electronic effects are in constant oppositional balance. They oppose each other, and which one matters more changes depending on atomic size. For example, if you consider this larger atom here, the electrons are able to space out such that the distance between a given electron and the nucleus is much closer than the distance between one electron and another. As a result, a new electron can be added nicely without increasing repulsions too much, even though we have a relatively weak nuclear attraction. Conversely, in a small atom, the electrons are tightly packed, and the distance between each other is similar to that of the distance to the nucleus. As a result, adding a new electron will increase repulsions significantly, but the raw attractive energy of the nucleus is greater than in the larger atom. The effect of this competition is pretty clear if you look at the group 16 elements. So we're going to go ahead and look at group 16 trends in electron affinity. Oxygen, which is very small, does have a very strong nuclear attraction towards the incoming electrons. However, its small size also means strong electronic repulsions. As such, when you move from oxygen to sulfur down the table, electron affinity actually increases. At this small size, the repulsions are dominant. Increasing in size to sulfur alleviates the repulsion significantly and allows for electron capture to become more favorable. However, as you continue to increase in size down the table, the electron affinity starts to decrease in magnitude, approaching zero again, because the attraction to the nucleus starts to fall off as the atom gets bigger and bigger and bigger. This trend means that period 3 elements actually have the largest electron affinities, not period 2 elements, which might be a little bit surprising since we think of period 2 elements as having the largest electronegativity and the largest ionization energies. But in fact, the competing effects between repulsions and attractions mean period 3 elements are going to have the highest electron affinities. Another nuance with electron affinity has to do with certain groups, namely groups 2, 15, and 18, which have particularly low electron affinities. In fact, some of these elements have positive electron affinities, meaning they would increase in energy should they accept an electron. These trends are a result of the fact that energy levels are not homogeneous, but consist of distinct orbitals of different energies, namely s and p orbitals for most of these elements. Let's consider group 2 first. Adding an electron to a group 2 element would mean the creation of a whole new sublevel. Consider the orbital diagram of beryllium as an instructive example. Currently, its valence electrons sit in the 2s orbital. A newly captured electron would need to enter into a 2p orbital, which is appreciably higher in energy than the 2s, so much so in fact that it cancels out the potential energy of nuclear attraction. This occurs for two reasons. One, the p orbitals are simply further away due to their probability distribution and experience a weaker nuclear pull. But although the 2s electrons are considered valence electrons along with the 2p, the 2s electrons will actually repel the incoming 2p electron like core electrons repel typical valence electrons, because the 2s are substantially closer to the nucleus. As a result, the electron affinity of beryllium will actually be slightly positive due to this electronic repulsion. The moral of the story is electrons don't want to enter a new higher energy orbital because of the electronic repulsions and larger distance from the nucleus. We see this even more clearly with group 18 elements, the noble gases. Adding an electron to one of these will result in the creation of an entirely new energy level. As shown in the orbital diagram here for neon, adding a new electron will result in the creation of a whole new n equals 3 energy level. It's very similar to the group 2 trend, but it's even more substantial. It's almost impossible to add an electron to a noble gas, and they're all going to have large positive electron affinities. They do not want an extra electron. Perhaps the most interesting, though, is the trend that occurs with group 15, and that has to do with the energy of electron pairing, specifically the repulsion of electron pairing. If you look at the orbital diagram for nitrogen, you see that it has a set of 3 unpaired electrons in its 2p orbital. Any new electron will have to necessarily pair up with one of these electrons. This significantly increases electronic repulsions within the atom, since these 2 electrons are now occupying the same spatial orbit, and this will counteract the energetic benefit of the nuclear attraction. As a result, nitrogen has an electron affinity that is essentially 0 kilojoules per mole. Another term of importance is known as the second electron affinity, which describes, as you guessed it, the energy associated with capturing a second electron in the original anion. Because one electron has already been captured, this anion carries a negative charge, which is going to repel any incoming electrons somewhat. So going from X minus and adding an electron to get to X2 minus is going to be a little bit difficult. The Coulomb repulsion due to the original X minus charge is going to make adding that second electron a little bit tough. In fact, polyanionic single atoms like O2 minus are quite unstable. For example, if you look at the actual energy values for oxygen, you'll see that the first electron affinity is negative 141 kilojoules per mole, which means that it is going to release 141 kilojoules when you absorb an electron. That's energetically favorable. However, adding a second electron is wildly unfavorable. It takes 780 kilojoules per mole to add the electron. You actually need to input this large amount of energy to form O2 minus. In order to have this occur, you need a large force to drive the reaction thermodynamically, right? So I really want to stress the positive value of the second electron affinity means that to form a salt, for example, like sodium oxide, Na2O, you're going to need a really strong driving force to form that O2 minus anion. So these are food for thought for later when we talk about the Born-Haber cycle for the formation of ionic compounds. Finally, I want to just go ahead and summarize the consequences of electron affinity and why it's so important. The single largest importance is that it is a thermodynamic counterbalance for the ionization energy needed in the formation of ionic bonds. Ionization energy requires an energy input, and the negative nature of electron capture means that it releases energy and helps make the overall process energy releasing, which is thermodynamically favorable. It helps drive the reaction forward. It's also important though because it gives us insight into how we can calculate the lattice energy of an ionic compound through the Born-Haber cycle calculations. And it also helps predict the Lewis acidity of different compounds. The Lewis acidity measures how receptive to electrons a given atom will be, which is sort of analogous to electron affinity. Finally, it also helps with certain instrumental techniques in mass spectrometry, which rely on electron ionization, and the values need to be known for those precise measurements. And with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you like what you saw, please go ahead and like and subscribe to the channel. To learn more, check out our other videos in the chemistry playlists, and if you're looking to branch out, check out our other science playlists as well. See you next time!